Welcome to this video lecture series on transportation engineering. In this session, we shall discuss on the factors affecting the rigid pavements. So there are various factors which affect the design and performance of the rigid pavement or the cement concrete pavements, which are as follows. First is the wheel load. Second, the temperature variation at the location of the road. Third is the types of joints and their spacings. And lastly is the subgrade and other supporting layers. So the two major factors primarily which are to be considered for the design of a rigid pavement, they basically are: firstly is the heavy traffic load, and secondly is the temperature variation between the top and the bottom of the cement concrete slabs. And the other factors which affect the design and the pavement of the performance of the rigid pavement are the temperature stresses due to the expansion and contraction of the rigid pavements during the summer and the winter season, and second is the volumetric changes in the subgrade due to the changes in the moisture and the temperature. And lastly is the loss of the subgrade support due to the some reasons or due to with the reasons at the certain location beneath the pavement. Now first is the wheel load. The performance of a rigid pavement and its service, it largely depends on the actual magnitude of the heaviest vehicle load of the heaviest wheel load of the vehicles and its number of repetitions during the design life of the pavement. So this wheel load of the highest magnitude, it will cause the flexural stress in the rigid pavement. And the important factors associated with these wheel loads are: firstly the magnitude of the load and the contact pressure of the loaded area. Second, location of the loading on the cement concrete pavement slab, where actually that wheel load it has been applied. And thirdly, the repetition of the loads of the different magnitudes during the entire design life of the pavement. So the next is the magnitude of the load. So the magnitude of the wheel load, it directly affects the stresses in the cement concrete pavement. Higher will be the magnitude of the load, which will cause the higher stress in the pavement. So the wheel load, it is expressed in the terms as follows. First, the total load P, it is taken in kg. Second is the contact pressure small p, it is taken in kg per centimeter square. Third is the contact area denoted by capital A in centimeter square, where it's calculated by using the formula pi into a square into p, where A, it is the radius of the equivalent circular area of the contact. As we have discussed earlier, that whenever a wheel it comes in contact with the pavement, then at the point of contact, the contact in between the tire and the pavement, it will be in a circular, it will be basically in an elliptical form, but for the design purpose it is considered or it is assumed to be as circular. Next, the location of the load applied on the slab. So the load stresses on the slab, they vary depending upon the location where the wheel load it acts. Following are the three locations which actually are considered in the analysis and design of the cement concrete pavements. Firstly is the interior load I, which is applied at a location away from the edges of the slab. Second, B, the corner load, that is C, applied at the corner region of the slab. And third is the edge load E, which is applied at the edge region of the slab. So the magnitude of the stress due to the given wheel load applied at the corner region is the highest in comparison to the stresses due to the same magnitude of load which will be applied at the edge or the interior region of the cement concrete slabs. The load stress which will be applied at the interior region of the cement concrete pavement away from the edges is found to be the lowest, as in comparison to the stress which will be caused due to the same load which will be applied at the edge and the corner regions of the pavement. Next, we shall discuss on the repetitions of the loads. So the repeated application of the light loads, they do not cause any structural deterioration in the rigid pavements. Therefore, it is essential to measure the load of the higher magnitude, which basically will be responsible, or they will cause the significant stress in the rigid pavements. So for this design of the rigid pavement, it is essential first to estimate the actual magnitude of the heavier groups of the axle or wheel loads. Second, to determine the flexural strength developed due to these heavy loads. And thirdly, it is to estimate the number of repetitions of each load group to use the road during the design life. So the repeated application of the high magnitudes of stresses, they are to cause the failures due to the fatigue in the cement concrete structures. The plain cement concrete specimens or the slabs, it can withstand against a number of repetition of the loads to cause the stresses, and if in this case the magnitude of the applied stress it is less than 44% by the flexural strength. Next is the stress ratio. So the ratio of the flexural stress due to the load applied on the cement concrete pavement to its flexural strength, it is called as the stress ratio. So from the fatigue studies on the cement concrete pavements, the number of repetitions up to the fatigue failure, it has been determined by using the various values of the stress ratio in between 0.45 to 0.9. So while designing a cement concrete pavement, if the stress ratio is less than 0.44, then there actually is no possibility of the fatigue failure. So from this table we can see the stress ratio and the fatigue life or number of repetitions up to the failure in the cement concrete. So the importance of stress ratio in the design load. So this repeated application of any load of magnitude which is less than the design load, it would cause lower stress ratios. Hence there will be no structural deterioration of the pavement due to this load. So the design wheel load, it should be decided very carefully by taking into account the wheel load distribution studies and the expected number of the repetitions of the load of the different magnitudes during the design life of the pavement. The movement of even a small number excessively over a loaded vehicle with the higher magnitude of the loads than the design load, it can develop the tensile cracks at certain locations in the cement concrete slabs. Hence, it is suggested that the axle load studies, they should be conducted on the heavy vehicles in order to arrive at a design axle load. And wherever it is necessary to estimate the possible movement of the overloaded vehicles with the loads exceeding the design loads. Next is the axle load distribution studies. So the axle load or the wheel load distribution studies, they are carried out on the selected heavy vehicles that actually are moving on the existing roads. So it is also desirable to note that the wheelbase or the spacing between the axles of the heavy commercial vehicle, that is the HCV, that is the heavy commercial vehicles, they have to be noted. So the objective of the axle load distribution studies is to arrive at the design load. Second, to assess the effect of the repeated application of the stresses due to the loads that are heavier than the selected design load, which would cause the stress ratios exceeding 0.44 and the number of repetitions of such heavier loads expected during the design life of the pavement. So this data, it is necessary at the design stage for the fatigue analysis of the pavement. Next is the determination of the design load. So for the in order to complete the measurement of the axle or the wheel loads on the selected samples of the heavy vehicles with a single, tandem, tridem or multiple axles at the identified locations. Next, the axle load distribution table, it is prepared by grouping the loads at the convenient load intervals or ranges. Then the average of all the load groups, it is taken as the magnitude of the applied load and the expected number of repetitions of the wheels or all the vehicles of each range during the design life, it is estimated, and then the total number of axle loads of each interval, they are noted during the project preparation, and studies are noted as the initial traffic. Now considering the different vehicle classes, their growth rate, the construction period and design life of the cement concrete pavement, the total number of repetitions of the load of each group load during the design life of the cement concrete pavements, they are estimated. And based upon the above data, the cumulative frequency distribution table or a diagram which will represent the load values and the total number of repetitions during the design life of the pavement, it is prepared. And from this table or the diagram, the 98th percentile load which would be exceeding by only 2% may be taken as the design load. So that 98th percentile load, it will be selected as a design load. So it is also desirable to consider a load safety factor of about 1.2 in order to account for the possibility of the further overloading of the heavy vehicles. Next, we shall discuss on the daily variation in the temperature. So the daily variation in the atmospheric temperature, it causes the difference in between the temperatures at the top and bottom of the cement concrete slab, and this results in the wrapping of the slab and development of the flexural stress. As you can see from the figure, during the daytime, the compressive stresses, they are at the top, whereas the temperature at the top, it is taken as T1, and at the bottom it is taken as T2. And at the bottom, during the daytime, we have the tensile stresses. Here in the daytime, the slab curved, which is curved down at as T1, there is a upward temperature which is exposed to the sun is more as compared to the temperature of the slab at the bottom, whereas it is exactly opposite as in the case of the night time. So the temperature difference between the top and the bottom of the cement concrete pavement, it will result into the differential expansion of the slab, which will cause the warp or the bend into the slab. The temperature difference during the day, it is given as T degree Celsius, which will be T1 minus T2, wherein T1 will be the maximum temperature at the top of the pavement during the day, whereas T2 will be the temperature at the bottom of the pavement during the night. So the temperature during the night time, so at the late night, top of the slab, it becomes colder as compared to the bottom of the slab, resulting into the wrapping of this slab. The temperature difference during the day, as you know, it is given by T degree Celsius equals to T1 minus T2, wherein T1 is the minimum temperature at the top of the pavement during the night, and T2, it is the corresponding temperature at the bottom of the pavement during the night time. So the no wrapping condition. So for this no wrapping condition, during the two short durations within the 24 hours, the temperature at the top and the bottom of the slab, if they are equal, then the no wrapping it will take place. So for the no wrapping condition, it is essential that T1 and T2 they both are the same. So at this stage of the cement concrete pavement, it is called as the no wrapping condition of the pavement. Next, we will be discussing regarding the stresses in the rigid pavement. So the different types of stresses developed in the cement concrete pavement, it consists of, first is the wheel load stress, which will be caused by the heavy wheel loads, and second is the wrapping stress, which will be caused by the temperature differential between the top and the bottom of the pavement. So it is possible to determine the stresses which will be developed due to the wheel loads, wrapping and the contraction of the cement concrete slab, and it is not possible to estimate the magnitude of stresses as a result of the volumetric changes in the subgrade. So the first case, for the wheel load stresses as per the Westergaard stress equation, the cement concrete slab, it is assumed to be homogeneous and to have the uniform elastic properties, with the vertical subgrade reaction being proportional to the deflection. So here the cement concrete slab, it is assumed to be homogeneous and it will have the uniform elastic properties with the vertical subgrade reaction which will be proportional to the deflection. So Westergaard developed the relationship for the stresses at the interior edge and the corner regions, and they denoted them as sigma I, that is sigma interior, the stress at the interior, sigma E, that is the stress at the edge, and sigma C, that is the stress at the corner region, which are denoted in sigma I, sigma E, sigma C in kg per centimeter square respectively, and they are given by the equation. So the load stress at the interior due to the interior loading sigma I, it is given as 0.316 into P upon H square in the bracket 4 into log to the base 10 multiplied by L by B plus 1.069. Then the load stress sigma E due to the edge loading, sigma E, it is given as equals to 0.572 into P upon H square multiplied by 4 into the log to the base 10 multiplied by L by B plus 0.359. And lastly, the load stress sigma C due to the corner loading sigma C is equals to 3P upon H square multiplied by 1 minus A into under root of 2 upon L bracket complete raised to 0.6, wherein H is equals to the slab thickness in centimeter, capital P is the wheel load in kg, A is the radius of the wheel load distribution in centimeter, L is the radius of the relative stiffness in centimeter, and B, it is the radius of the resisting section. So from this figure we can see the critical stress locations of the slab. Firstly, the tension at the bottom for the stress at the interior portion, then at the edge portion, and lastly the stress at the corner loadings, that is sigma I, sigma E and sigma C. So again, the maximum stress produced by a wheel at the corner, it does not actually exist around the load, but it occurs at some distance x along the diagonal. So this distance x from the corner, it is given by the relation as x equals to 2.58 multiplied by under root of A into L, where x is the distance from the apex of the slab corner to the section of the maximum stress along the corner bisector or the diagonal in centimeter. A is the radius of the wheel load distribution in centimeters, and L, it is the radius of the relative stiffness in centimeters. So this was in regards with the Westergaard's theory of the stresses induced by the loading at the interior, edge and the corners. So with this we shall stop. Thank you.